Hello, we are Team MST Mongol Barota from Bangladesh, excited to embark on our journey to the University Rover Challenge 2025, introducing our rover AURORA X assisted by our drone Genesis 2.0. This year, we adopted a differential bar system with a modular stainless steel chassis, which weighs about 46 kilograms with arm and under 50 kilograms with science module. Its robust design absorbs frontal and rear impacts, ensuring rock-solid reliability even in the MDRS's rocky terrain. The rocker arm geometry and low center of mass enable the rover to climb 45-degree inclines and traverse 35-centimeter obstacles even on sandy or uneven terrain. Aurora's four-wheel drive system features 3D printed TPU wheels refined from last year's geometry to reduce stiffness by 30% and enhance traction via 20% wider tread contact. Custom rims and shafts ensure seamless integration with 24-volt DC motors for optimized torque transfer. All machined components have been fabricated in our institute lab. 5DOF rover arm is built from parallel links of aluminum alloy with optimized strength-to-weight ratio. Additionally, the arm is articulated with feedback actuators for differential inverse kinematics and precise motion. Its geared stepper-driven end effector enables lifting and carrying up to 6 kilograms and extends 1.5 meters. It operates a 4-position spring-return joystick due to its refined dexterity, which is further highlighted by turning knobs and rotating hex nuts. Moreover, the arm is adept at handling delicate tasks such as inserting and removing pen drives and plugs and executing precise button presses and switch flicks. Additionally, the rover arm can open panels and drawers as well as grasp and transport objects of various shapes and sizes. For autonomous typing, a custom model is trained to recognize letters and predict their 3D spatial coordinates. New this year, Genesis 2.0 supports the rover by scanning fields, reading signs, and locating objects in areas with poor radio reception during the delivery mission. Its payload deployment mechanism can place objects up to 1.2 kilograms beyond the rover's reach. Our electrical team focused on enhancing the reliability and robustness of our rover's power system. We have developed a custom battery pack composed of LiPo cells, collectively providing 24 volts. An integrated battery management system monitors battery temperature, voltage, and current flow while enabling automatic cutoff during low voltage conditions. To facilitate real-time monitoring, we have redesigned our electrical dashboard to display all power metrics. Additionally, we upgraded our previous power distribution board to ensure a stable and enough current supply to all subsystems. Last year, we used 2 separate PCBs along with 2 microcontrollers. However, this year we have consolidated all functionalities into a single PCB, optimizing the efficient use of our Teensy 4.1 microcontroller. Furthermore, we have incorporated an accessible and visible kill switch of high current capacity to allow instant power cutoff when necessary. Based on several test data, we have introduced a new automated rotating mount for our directional sector antenna to ensure longer range connectivity compared to last year. Additionally, we have an omnidirectional antenna as a backup for Wi-Fi. For control, we're using a 2.4 GHz S-bus radio signal with Wi-Fi as a fallback. Additionally, this year we have implemented a control system capable of automatic switching between radio and Wi-Fi, ensuring zero delay in case of any connection errors during the mission. For vision, we are using 2 FPV cameras with a 5.8 GHz transmission protocol as a primary video feed, while 2 IP cameras operate on a 2.4 GHz IEEE 802.11 protocol as a secondary. For data transmission, our system primarily relies on Wi-Fi, with radio serving as a backup. We have ensured N+1 redundancy for data transmission, control system, and video transmission, an improvement over last year. After thorough testing and research, we have made several major improvements compared to last year. We are now using ROS 2 and ROS 1 simultaneously on the Raspberry Pi 5 and Jetson Xavier NX. To enhance localization accuracy, we have integrated an RTK antenna and a differential GPS combo fused with an IMU, achieving precision up to 2 centimeters. This GPS navigation stack is a proven system successfully validated during our autonomous mission at ARC 2024 in Turkey. Our dashboard enables waypoint-based navigation, allowing operators to set waypoints, initiate traversal, and receive real-time updates on the rover's positional metrics, including latitude, longitude, and orientation. Spiral and square pattern searching techniques are tested this year to locate AR tags using the Z2 depth camera. Our standalone AR tag detection package can identify tags from a distance of up to 12 meters in normal daylight. Once detected, our navigation stack follows the tag and guides the system to within 2 meters of it. A flashing green LED indicates successful traversal. We've also developed a custom YOLO model, trained and tested to detect mallets and bottles. Unlike last year, we've successfully tested the rover's abilities to autonomously search for and identify these objects. This year, we are using an auger drill to loosen the soil before deploying the scooper to reach subsurface soil at a depth of 10 centimeters. As a new addition, we have integrated an NPK sensor to measure subsurface temperature, humidity, pH, nitrogen, phosphorus, and potassium levels. Additionally, we have incorporated an onboard environmental monitoring sensor to measure ambient pressure, temperature, and humidity. All sensory feedback is displayed on our science dashboard in real time. The collected soil, retrieved using the scooping mechanism, is filtered from rocks using a strainer and then deposited into a beaker carousel. Biomolecules in the sample are identified through Benedict's and iodine tests for carbohydrates. To ensure proper reagent supply, we're using 4 peristaltic pumps, an improvement over last year. An additional heating rod has been incorporated to facilitate the Benedict's test, and a gas sensor is now used to detect the presence of ammonia. Our dashboard enables the execution of chemical and rock tests. Chemical test outcomes are processed by our custom algorithm, classifying samples into 3 categories: extinct, extant, and no presence of life. A digital microscope with an adjustable zoom mount is used for onboard rock surface inspection and analysis. To enhance classification accuracy, we have trained our model with 2,000 additional rock samples this year, increasing its accuracy to 92.6%. Moreover, we are introducing a Raman spectrometer for mineral and soil sample analysis, featuring improvements in laser power, spectral range, and CCD sensitivity, achieving better spectroscopy performance than last year. As part of our STEM engagement program, we conduct workshops and seminars in high schools and provide hands-on training in space robotics to students from other universities. We look forward to seeing you in Utah this year. On behalf of our team, thank you for your time and best of luck to all the teams.